resistors in parallel. So this is what you did in the second part of the lab. So what happened? All the bulbs were the same brightness within any given circuit. So that means you had to have the same voltage drop across each, because for any charge carrier, right, moving from the one terminal of the battery to the other through a complete circuit, has to have the same potential drop. So it doesn't matter which path it took, it had to have the same drop in potential, so the same voltage. And if they're all the same brightness, we know that means that they all have the same current. So the equivalent resistance must be something different than just adding up the resistance of each of them, like we saw in series. And since charge is conserved, the total current through the battery, so coming out of the battery or going in, it must be more than through any individual resistor, because my electrons, I have some number of them coming out of the battery, and then they have to choose a path, but I haven't created any more electrons or gotten rid of any, and then they have to come back together to get back to the battery. So let's look at a particular case of resistors in parallel. Like this one. This was circuit 2 on the second part of your lab. So we're going to say that each one has voltage V, all right, some potential difference between the two ends of it. It's got half of the current coming out of the battery and some resistance R. We're going to say, just like the light bulbs that we used in class, they're equivalent resistors. All right, for a whole circuit, all right, take the whole thing. It's got some voltage source, right, that same V. It's got a total current, and we want to know its equivalent resistance. Now, you haven't seen this equation yet. We'll get there in the next video. So don't worry about this. It'll make a little more sense later. I'm just showing you how you derive this in general. Okay, so for the total circuit, okay, my voltage equals I times the equivalent resistance of the circuit. Okay, but for each resistor, which has the same V, so I can still call it equals, it's 1/2 of I times R. Well, that means if I simplify all this, I can get the equivalent resistance is equal to 1/2 R. So having two light bulbs in parallel meant that I had less overall resistance than just one. Maybe that's why the light bulbs actually kind of got a little bit brighter when I put more light bulbs in like this. This particular case only works for two identical resistors. Do not memorize anything on this page. Okay, so in general, for resistors in parallel, here comes the equation you need to know. 1 over the equivalent resistance of a circuit is equal to the sum of 1 over the first resistance plus 1 over the second plus 1 over the third. Now, this is the hardest equation for the unit, only because you have to add fractions together, and then you have to remember that on the left it's also a fraction, so to actually solve for the equivalent resistance, you have to invert your final summation on the right. Remember, when you add fractions, all right, you cannot add a fraction that has a different denominator. That's the one on the bottom. So you have to convert them all to the least common denominator, and then you just add up the numerators, and that's how you add them. Okay, here's the sample problem. For this circuit, I want to know what the equivalent resistance is of the whole thing if each resistor has resistance R. Okay, so I know that 1 over my equivalent resistance is 1 over R plus 1 over R plus 1 over R, which I can simplify as 3 times 1 over R, or 3 over R. So I flip both sides to get the equivalent resistance. That's the tricky part. Don't forget to invert after you've added up all the fractions. All right, so my equivalent resistance is just 1/3 of R, or R over 3.